7.7, Improper Integrals. Now, we're working our way through Chapter 7, entitled Techniques of Integration. This section isn't so much about a new technique of integration as it is a new type of integral for us to evaluate. Although certainly there will be special ways for us to evaluate these integrals that we haven't looked at before. So, what's going on in this section? Well, let's just remember what we've looked at before for definite integrals with Riemann integrals. So I'd say to you, integrate from a to b f of x dx. There's a couple requirements there, that we're assuming that a and b are both finite numbers. And we're also assuming that our function is bounded between a and b. And so if we meet these and maybe, let's say something about continuity, then we can interpret this integral as simply an area under the curve. But there's other kinds of problems that we can think about. So for instance, what happens if we have a function that looks like this? It has a asymptote here, a horizontal asymptote it's getting closer and closer to 0 as the function goes to infinity. Can we compute the area under this curve as this goes off to infinity? Now it might turn out that this is a infinite area, but there's also some ways in which the area, depending on what exactly the function of this curve is, will actually turn out to be finite. And so this is something, this situation is something that we'll want to consider. Apart from having, so here we're messing, in this example, we're messing around with the bounds being finite. If we mess around with the function itself being bounded, maybe a function that looks like this. So, perhaps we wonder, what's this area here? So here we have a vertical asymptote. And once again, we'll want to be able to compute this area under this curve in some limiting sense, and maybe it's finite, maybe it's infinite, but these are questions that we want to consider that just can't get covered by original Riemann integral definition. So we run into these cases or other similar cases. This is what's known as an improper integral. And so here's a formal definition, carefully copied, about what it means, what is an improper integral. So, in the first case, we're going to be looking at the case where the upper bound is infinity. So, fix number a, assume that f is integrable over the interval from a to b for all b bigger than a. Then we define an improper integral of f over a to infinity as this following limit. So the integral from a to infinity of f of x dx is, we replace the infinity with an r, or some other letter. Nothing special about using a capital R there. And so we integrate from a to r of f of x dx, and then we take the limit of that as r goes to infinity. And so there's a limit here. We know limits sometimes converge, sometimes diverge. And so we'll use the same terminology here. We'll say that this improper integral converges if this limit exists, which means the limit converges, and we'll say that the improper integral diverges if this limit does not exist, if the limit diverges. So this is a definition for the improper integral is from a to infinity, fx dx. Similarly, we can define the integral from negative infinity to a, fx dx, as a limit of the integral from r to a, fx dx, as r goes to minus infinity. So this is a definition an initial definition of the improper integral. It'll cover some cases. In fact, it basically only covers this first case that we'll look at in this section. So we'll look at 4 types of improper integrals in this section. First is when one of these limits is either plus or minus infinity, but not both. We'll also look at some examples where both of these are infinite, minus infinity to infinity. Then we'll also have to look at the vertical asymptote case. So going back to this picture, what happens, we have a vertical asymptote at either one of the endpoints. And then last, what happens if there's a vertical asymptote in the middle? So we'll take turns looking at each one of these types in turn. Okay, so to wrap up this video, let's do an initial example here. Let's evaluate the integral from 0 to infinity of e to the minus x dx. Okay, so how do we do this? Going back to, let me get the slide back here. We're going to replace that infinity with an r and take a limit as r goes to infinity. So this is going to equal the limit as r goes to infinity of the integral from 0 to r e to the minus x dx. So the antiderivative of e to the minus x is minus e to the minus x. Plug in 0 and r, still keeping that limit there. Limit as r goes to infinity of minus e to the minus r plus e to the 0, which is going to be 1. And so now let's think about what happens here. As r goes to infinity, e to the minus r goes to 0. So this will be 0, this will be 1. And so that says that this answer is 1. So let's go back to, let's just draw a picture here. E to the minus x, it looks something like this. That's an asymptote as we're going off to infinity. That's approaching 0. And so the limit of this area, what we just have here is that the limit of the area under the curve as the right endpoint goes off to infinity is 1.